Let us begin our discussion with asymmetric encryption. It is a method that uses two distinct keys for securing data, one for encryption and another for decryption. First key is shared openly with anyone who needs to send an encrypted message. Because it is available to all parties, it is referred to as a public key. Any message encrypted with this key can only be decrypted by its corresponding private key. This private key is kept secure and confidential by the recipient. Only the holder of the private key can decrypt messages encrypted with matching public key, ensuring that sensitive information remains protected. In summary, asymmetric encryption provides a secure way to exchange information by separating the encryption and decryption processes, making it a powerful tool for secure communication. Let's walk through how asymmetric encryption works with a simple example. Imagine user A wants to share a document with user B. In asymmetric encryption, user B begins by generating two keys, a public key and a private key. As name suggests, user B shares the public key with anyone who wants to send him a message, in this case, user A. Next, user A applies user B's public key to encrypt the document and then sends the encrypted message to user B. Finally, upon receiving the encrypted message, user B uses his private key to decrypt it and access the original document. Now let's consider a potential security scenario. If someone intercepts the public key while it's being shared with user A as well as the encrypted document while it's being sent to the user B, they won't be able to decrypt the message. Why? Because the public key, when applied again, only re-encrypts the message. Decryption can only be achieved with user B's private key, which is never shared and remains secure with user B. This ensures that even if someone gains the access to the public key and the encrypted data, they cannot decrypt the message without the private key, maintaining security of the communication. At a higher level, asymmetric encryption can be broken down into three key steps. First, create a pair of keys, one public key and one private key. Second, encryption. Use public key to encrypt the message. Third, decryption. Use private key to decrypt the message. Let's start with the first step, that is generating key using RSA algorithm. The RSA key generation process begins with selecting two large prime numbers, typically 1024 or 2048 bits in length. These prime numbers are crucial to the security of the RSA algorithm. Then compute the product of these two prime numbers. After this, calculate the totient, which is the product of first prime number minus 1 and the second prime number minus 1. Next is to generate the public key. Public key is an integer that meets the following criteria. First, it should be a prime number. Second, it should be less than totient. Third, it should not be a divisor of totient, which means that public key modulus totient not equals 0. Similarly, private key is determined by satisfying the equation, which is private key multiply public key modulus totient should be equals 1. Let us start with the implementation of asymmetric encryption. First, let's define the package named asymmetric encryption and define a class name generating RSA keys. Let's begin its implementation by defining a main method. RSA key generation itself contains number of steps. Let us start with the implementation of them. First step is the selection of two large prime numbers, typically 1024 or 2048 bits in length. However, in our implementation, we will going to use smaller numbers. Here we have selected two prime numbers, one is 7 and another is 19. Next, jump to the second step, that is compute the product of two prime numbers which we just defined. Next step is the calculation of quotient. Quotient is the product of first prime number minus 1 and second prime number minus 1. Next step is the computation of public key. Let us define a method which we are going to compute the public key and return the same. Now, as we know, public key should meet following criteria. First, it should be a prime number. Second, it should be less than quotient. Third, it should not be a divisor of quotient. As we can see, we require quotient in this particular method. Thus, let's pass quotient as an argument and define it as a parameter in the method definition. For the simplicity, let us define an array of prime numbers. Let's look through the prime numbers and try to find a prime number which satisfies rest of the conditions. So the first condition, it should be less than quotient, and the second condition is that it should not be a divisor of quotient, which means quotient modulus number should not be equals to 0. As soon as we hit that particular prime number, we will going to return the same. In case we look through all the prime numbers and we couldn't find the one which satisfies our condition, we will going to throw a new exception. At this particular stage, we are having public key. Now move to the next step, that is compute the private key. Again, let's define a method which we're going to compute private key. Let's define the same method. Again, as we now know, our private key should follow the one condition, which is private key multiply public key modulus quotient should be equal to 1. Thus, from this condition, we now know we need public key, quotient, both as the parameters to calculate the private key. Now let's loop through the numbers. Say we want to loop through first 1000 numbers and try to impose the same condition on that particular number, which is if that number multiply the public key modulus quotient equals 1. In that case we got our private key and we were going to return the same. In case we couldn't find our private key, then we were going to throw a new exception. At this particular stage, we are having our private key as well. Let's print both public and private key in the console. Let's put some paddings and finally let's execute our code. Now from the output in the console, we can say for the selection of two prime numbers, that is 7 and 19, we have our public and private key pair, which is 11 and 59. Now to find another pair of public and private key, we can alter the array of prime numbers. Say let's remove 11 and try to execute the same code again. And we got our new pair of public and private key, that is 13 and 25. Further steps, that is process of encryption and decryption using RSA algorithm, are straightforward once the keys are generated. To encrypt a message, apply the operation on the message bytes, which is message power public key modulus product of prime numbers equals encrypted message. To decrypt the message and recover the original text, use the private key as encrypted message power private key modulus product equals secret message. Now we already know the process of encryption and decryption using RSA algorithm. Let's try to write a method which will validate our generated key pairs. Let's first try to execute the code and generate a new key pair of public and private keys. In this case, first pair is 11 and 59. Let's write a method that is validate key pairs. This method will going to validate the generated key pairs. Let's define this method now. This method will going to accept public key, private key. Let's write the condition which will going to generate an encrypted message. So encrypted message equals message whatever we want to send power public key modulus product of the prime numbers. From the definition, we got to know that we also require product as in parameter. Let us pass all of them. Okay, so let's encrypt the message. So let's first define the message. I'm going to use big integer since it has capacity to store big numbers. Say our test message is say 60. Let us define our modulus number, that is product of two prime numbers. Now let's start with the encryption of the message. From our condition, it would be message power public key modulus product. Encrypted message or cipher text equals test message power public key modulus are product of two prime numbers. Let's print the cipher text in the console. Similarly, the process of decryption is ciphertext power private key modulus product of two prime numbers. So this formula supposed to decrypt our ciphertext to the original message. Let's see the same in practice. Let's print the original message as well. Okay, let's execute the program. So in this case, we have generated a pair of keys, a public key which is 11, private key which is 59. The original message which we want to encrypt is 60. The ciphertext, that is encrypted message, became 86, and after applying the private key we are able to retrieve the original message which is 60. At this particular point we have fairly good understanding how to encrypt single byte using asymmetric RSA algorithm. Let's try to implement the same algorithm to encrypt the whole string. For this, let's write a new class, say asymmetric encryption, and define a main method in it. Now I will going to use a whole new different key pair of public and private key. Public key is 29 and private key is 41 in this case, and product of two prime numbers which has resulted these two keys is 133. Now suppose a user want to send a string, say some secret message, to another user. Then we already know the recipient will going to share the public key to this particular user to encrypt this particular message. To encrypt this particular message, we first need to convert this message into byte array. Here at this particular line, I have converted this message to a bytes array. Now I will try to encrypt this particular string. Let's try to loop through all the bytes. Here I'm trying to convert this byte into big integer and trying to put the condition which will convert this byte into the cipher text. And finally add this particular cipher text into the list of the encrypted message. At this particular stage, we have already encrypted this string into the encrypted message. This encrypted message is being sent from one user to another user. The recipient requires this private key to decrypt this particular encrypted message. Let's try to decrypt this message using private key. Now I will loop through each element of the encrypted message and apply the operation to decrypt the same. And finally, I will going to print the decrypted message in the console. Let's put some paddings before we execute our code. This is the message which one user has sent to another user and encrypt the same message via asymmetric encryption. And this is the decrypted message which we are having after performing all those operations.